It's an interesting day. So yeah, I put together a little website, a GitHub repo for today, and I guess before we punch in the URL, but I was thinking we could just start by just going around and saying, introducing ourselves, and then just briefly saying what kind of research you're interested in, and maybe, of course it doesn't have to, but if you imagine, maybe that research could be aided in some way, or maybe not, by photochemical and climate modeling. So I can start. I'm Nick. I'm Nick Wogan from NASA Ames. Were you here on Monday? Oh, yeah, you guys, okay. Yeah, I'm studying exoplanet atmospheres using photochemical climate modeling, and I use photochemical climate models, like the model we're going to talk about today, PhotoChem. I use it a lot for basically all my projects. So Kayla, you want to?
Yeah, I'm Kayla. I am a first year grad student here at Planetary Science, curriculum Mark Marley, and I'm working on brown dwarf habitable zones right now, but hopefully my thesis work will lean more towards brown dwarf atmospheres and exoplanet atmospheres. In undergrad, I actually worked with kinetics.
Oh, you did?
Yeah, so I'm still like finishing up a project using kinetics. So I did undergrad research for about 3 years and just working with kinetics. So photochemistry is a special place in my heart, and I know I'll probably use it again throughout my graduate school career.
That's awesome.
My name is Matthew Murphy. I'm a graduate student over at Stewart, going into my final year. I primarily do observations of exoplanet atmospheres. And a lot of my work is kind of looking into photochemical products in atmospheres and how they're distributed and how things change with population. And so I thought having some ability to look at the chemistry myself would be very useful to that.
Are you like photochemical products, like the recent SO2 detections, like this? Okay,
Yep.
Cool. Nice. That's awesome.
Hi, Bruce Lauer. I'm an assistant research professor at Stewart. Work with Matthew and mostly lately on GOC observations. And so I'm interested in chemistry, hot Jupiters and subneptunes.
You're in the manatee.
Yeah.
Oh, you're both in the manatee. Okay. Yeah, I've seen your names on those papers. Yeah, that's a cool project.
Yeah, and I'd be interested also like GA 1214 and the subneptune.
Yeah.
Photochemistry does.
Yeah.
About it later.
Yeah, that one's a bit of our plan. But no, yeah. Interesting stuff happening there. Can you hear us?
I saw that she made something in the chat.
Let's see.
Something.
Here we are. Oh, I'm going to type my intro because I'm still actively weeping, but I'm interested in applying complex systems. Complex system science, exoplanet atmospheres to develop potential biosignatures. Chemical network biosignatures. Fan of your work. Great stuff. So this is sort of the GitHub repository for this workshop, and it's got a ton of tutorials in it. And here is our rough schedule, which can be adjusted based on our interests, but we'll generally track this. So just for starts, I'm going to give a little presentation which just tries to start from square one. What is photochemical modeling? What is climate modeling? What equations are we solving? Not diving into the nitty gritty, but just to show where we are starting and the motivation for it all. And then we're gonna install the PhotoChem software, which apparently some of you have already done. Jump the gun. And then we're gonna go over a couple tutorials. So for starts, just to get a feel for the model and how it works, model for the photochemistry of modern Earth. And that'll be like a live coding thing, so, we'll have, is everybody familiar with Jupyter notebooks? Yeah, okay. So we'll have a notebook open and, I'll be, demoing it and, you can follow along if you want, but you can also just watch. Cause each of these folders has 2 notebooks in it, so if I click on Modern Earth Photochemistry, it has a notebook that is blank. Right here, and we're gonna start with that. Move on from there in the workshop, but then there's also a completed notebook that has essentially where we're trying to go, and the things that I'm trying to communicate. So you can just follow along on that completed notebook, or you can type along on the uncompleted one. And then there's completed and uncompleted notebooks in each of these directories. So after the Modern Earth, well, obviously we'll just take breaks whenever we want. This 3 hours is super long. But yeah, take breaks, and then the next will be a little climate modeling tutorial. So for most of the people in this room, this will probably not be the most relevant because this is going to be for rock. So for the photochemical model can be applied to gas giants or rocky planets, and that's great. But this climate model is designed for rocky worlds. So there's other great codes out there for like Mark Marley's code and for simulating the climate of gas-rich planets. But still, we can do that. And then to finish it off, I was thinking we could do a model TRAPPIST-1E. So we model the climate and the photochemistry of TRAPPIST-1E. And we'll see when we get there. I mean, if folks are, I think that would be a great thing to do. But if folks are more interested, we might be able to do both. But I do have another notebook about modeling gas giants and brown dwarfs. So maybe we can just move to that. But I think we should, regardless, let's start with Modern Earth Photochemistry, the climate tutorial, and then we're gonna see where we're gonna go. Okay, so. Okay, yeah, so the model that we're going to talk about today is called PhotoChem. It's a flexible 1D photochemical climate model for planetary atmospheres. Yeah, so what is this model? In a nutshell, this software contains a one-dimensional photochemical model capable of simulating a wide range of planetary atmospheres, so rocky planets, Neptunes, hot Jupiters, hopefully any planet with photochemistry. And then there's also a climate model in this software that is designed for rocky worlds. And then there's also a chemical equilibrium solver. And the equilibrium solver is important for gas giants, getting initial conditions, stuff like that. And just as motivation, right, these photochemical climate models predict the chemical composition and temperature structure of planetary atmospheres. And I know you guys are a lot familiar with this and understand that it's relevant to our research. But yeah, it's useful for all sorts of stuff, like understanding exoplanets, the early Earth atmosphere, the solar system atmospheres. Yeah. Okay, what is a 1D photochemical model? In words, a 1D photochemical model is a description of how atmospheric chemistry changes over time from vertical gas transport, chemical reactions, and other atmospheric processes. And then in math, it's just solving this is a large system of partial differential equations. So on the left-hand side here is the rate of change of a gas or species concentration. And gas concentrations change over time because of vertical transport. Gases move up and down in the atmosphere from, essentially convection or turbulent mixing, and they also are transported by molecular diffusion. And then gas concentrations change because of chemical reactions, production and loss, and all sorts of other processes. So condensation, or the effects that rain has on our atmosphere, that is important, or any number of source or sinks of that gas that you want to incorporate. And this equation here is like a very classic partial differential equation that people solve for all sorts of applications. It's a reaction diffusion equation. Shows up, I think, in a lot of biology applications. So in photochemical modeling, we're often interested in steady states to the system of PDEs. Meaning, right, you might have some atmosphere that wants to change over time. And so what we do is we try to solve for the atmospheric state where change is not happening, where this equation is equal to 0, there's no change. And of course, there's still reactions happening in the atmosphere. Things are getting produced and destroyed, but all that production and destruction is balanced. You don't have an atmosphere that's changing all the time. And the reason for this is because we consider steady states because most atmospheres are in quasi-steady states. Like the modern Earth's atmosphere, like the ozone, important photochemical product, oxygen, chemistry. It changes over time. You put chemicals in the atmosphere and it makes an ozone hole, but generally speaking, it's in a quasi-steady state. And so it seems reasonable to model exoplanets as well in this way, where we assume they're not really changing a ton over time, which this can be wrong in some cases, but maybe reasonable in most cases. Okay, and just here's a picture of what a photochemical model is in the context of like a rocky planet. So here I'm imagining just a planet like Earth with an ocean. For a planet like Earth, chemistry is driven by ultraviolet light. Like that's, Earth is cool. And so a lot of the chemistry that happens is driven by UV photons. In the case of a gas-rich planet, there's a lot of the chemistry is driven by sort of the gas quenching at depth. Like that's really determining the whole composition of the atmosphere. And also we're going to talk about climate modeling. So what is a one-dimensional climate model? In words, it's a one-dimensional climate model. And it computes the temperature structure that balances radiative and convective transport. And it solves this other system of partial differential equations. Well, this is actually just one partial differential equation. And it's the rate of change of temperature on the left-hand side is equal to how radiative energy is transported vertically in the atmosphere, and also how convective energy is, or how convection transports energy. And just like with photochemistry, we're typically interested in steady states where we're balancing radiative and convective energy. And of course, this is an approximation, right? Earth is in a quasi-steady state, but then there's climate change. So these things aren't perfectly balanced for Earth, but they're very close to balance. Obviously you can really, like with any system of PDEs and there's so much to solve these equations in computers. You need to discretize them using methods like the finite volume method or finite differences, and those details are in.
Hello, James Webb. You must be Nick.
Yeah.
Yes,
Yeah.
Nick, good to meet you.
Yeah.
Sorry for getting you late.
Oh, no, yeah. We're just doing the introductory presentation, but yeah, you haven't missed much. But yeah, just if you're interested in getting into the weeds and understanding these derivations of the photochemical equations or the climate equations from first principles, my Catlin and Casting 2017 textbook is really good. There's 2 appendices on this, and then in the appendix of my PhD thesis, I try to start from a statement of conservation of math, and then work our way all the way to the discretized equations that you put into computers. And obviously it's deep in the weeds. You don't know kind of list research questions for questions. So yeah, the photochemical model is called PhotoChem, and it's on GitHub. It's open source, and anybody can obviously use it. And so all the source code is on here. Cruise through it. It's written largely in Fortran. It's not scary old Fortran. Fortran 77.
That's easy.
It's easy. Well, in many ways, old Fortran is simple. Yeah. But so it's written in new Fortran. It looks a lot like Python. Or there's classes, objects, and these sorts of things. Yeah. And but then it's all used. I always use it via a Python wrapper. So Python is this incredible thing that allows you to glue Python to virtually any compiled language. Remarkable. So there's a Python wrapper.
I have a quick question.
Yeah.
If it's still mostly using Fortran, does this mean it still has Atmos's weakness of not being able to use stoichiometric coefficients in the reactions list?
No, it does not. So.
Oh, thank God! I always hated that.
Absolutely, yeah. So with the newer Fortran, it's everything is flexible. So there's older codes like Atmos or other older photochemical models where there's and you guys I'm sure you're familiar with these, where there's compile time constants. Where you're not familiar. Oh. So when you compile the code, an array must be this size. It only can be size 10. But what if you want to make, and let's say there's 10 reactions, so this array must be size 10. What if you want to add an 11th reaction? Then you're out of luck. You need to recompile the code. You can't just allocate another chunk to that array. And so there's all sorts of, it makes a challenge. So this is not that way. There's everything allocated. It's easy to install, so we're gonna go over this in a moment, but all you guys used Conda before, Conda install stuff? No, yeah. Yeah, so it's just Conda install NumPy, Conda install PhotoChem, and it works on Mac and Linux.
It's on Linux.
Oh yeah, Mac and Linux, but not on Linux. No Windows computers here, right? Is that a Windows?
It is a Windows,
Yeah.
but I have a virtual.
Windows subsystem for
Yeah.
Linux. Okay, yeah, that works great.
So it's Windows technically.
No, that'll work. Yeah. Okay. Oh, I have my hand up. That happened. Okay, and so heritage of PhotoChem. So all of I think, like anything, it's just these codes, they come from a long line of other codes that we learned from. Like I think about like Mark Marley and his climate model that's been around since, I don't know, 30, 20 years or something like that Taylor works with. And the same deal with PhotoChem. So back in the 1980s, Jim Casting and Kevin Zonley, they made a photochemical model, and they used it for some like classic publications. Like Kevin Zonley did his PhD thesis in '85, and then wrote a couple papers, photochemical papers just after that. And then Jim Casting also created a 1D climate model as well. And then throughout the 1990s and the 2000s, these models were developed and they were used in like a lot of pretty classic publications. So like there were the first habitable zone, some of the first habitable zone calculations. This the climate model was used for, and also calculations of the early Earth and the likely oxygen and ozone on the early Earth were from Jim Casting.
So Nick, let me ask you a question. So I used this old model of Jim's. I adapted it to a solar nebula, so I kind of ripped the whole thing apart. One thing I've always wondered is that old model, I don't know what the later ones from the 1990s, but from the 80s, it only had an eddy diffusion coefficient. There wasn't any molecular diffusion.
Oh, really?
And yeah, so I'm just wondering, is there a version of the old one in which they actually did put in?
Eventually, yes. I'm not sure. I mean, I know. So going forward in a timeline, there was this Mark, Claire, and other people. They put together Atmos, where they put together the 1D climate model, the photochemical model, and that version I've seen molecular diffusion. So I guess
So that means they have a version of just the photochemical code that has diffusion.
or edit.
Yeah.
Or,
I mean, it's not a huge add to put it in, but it's something.
yeah.
Change the equations.
Yeah. So in this 2015-ish version, this is one small Atmos was put together.
It's still Fortran 77.
Yes. It was, I don't know, like I just, in my world, I feel like worked with a lot, as a grad student, and I worked with a lot of codes that were like worked on 30 years. And they changed, but they're still written in Fortran 77. Is this not your guys' experience?
Not so much,
Oh, really?
but I think that's more a function of like what specifically you do for your research.
Yeah.
So I kind of grew up on like just built Python packages for lecture.
Yeah.
So I learned Fortran like through the education system, but skipped over having to actually really use it.
To wrestle with it, yeah.
Okay, so it's all I've used, and I hate wrestling with Python.
Yeah.
But this is a function of age.
I'm having a very fun experience. So at NASA Ames, I work right next to Kevin Zonley, and he's now learning Python for the first time.
Mark's like, I don't know Python.
Yeah. And so he's like, okay, notebook, what's a notebook? Like
Yeah, it's so different. I mean,
Yeah.
the organization is just wild. It's totally different language.
absolutely, yeah. And he's determined that I think it's gonna work out. So yeah, I mean, there's been all sorts of developments of Atmos. Like one maybe
PL for.
there's a virtual planetary laboratory at University of Washington.
Yeah.
And they use that code for a couple recent like James Webb observations, like their the observations of TRAPPIST-1c. They use their climate photochemistry, this photochemistry.
So is that version available also? Is somebody put it on GitHub or is it somewhere?
The VPL one is not, but this one is. and it's on the Virtual Planetary Laboratory GitHub. If I Google Virtual Planetary Laboratory Atmos, it pops up.
But the VPLs are,
But not the detail. Yeah, it's confusing, isn't it? This one is like more or less maintained by folks at Goddard. Like Sean Goldman had a group. He's sort of moved on in his role, I think, but long story short is there are folks at Goddard that work with and develop this sort of Atmos, the Atmos code. And so then in late 2020, I created a Python wrapper to Atmos, to the photochemical parts of Atmos. And I called that PhotoChem. And then in my projects, I was facing some challenges where I couldn't figure out how, I just couldn't figure out how to do it with the older code. So then in April 20th, 2021, I started building the code from the ground up. So
wait, I'm curious, but if you don't mind saying, what were you not able to do?
So one of the challenges was like, I had this project. I had a project on the Earth, so like on Monday, I gave a presentation, and we were looking at the atmosphere after big impacts, and these atmospheres were like, they were hydrogen dominated, and then they would transition to CO2 rich. And they didn't have a constant surface pressure, there was hydrogen escape over time. And so with this older version of Atmos, the equations are derived such that you assume a surface pressure, and you also assume a background gas. So you say the background gas is nitrogen, and the surface pressure is 1 bar.
That all comes from the original code.
And this, yeah, that comes from derivations back here that make it. And so then a couple of years ago, I just rederived the equations, and I didn't want the assumption of background gas because I was modeling this transition from a hydrogen atmosphere to the CO2 atmosphere. And I wanted the pressure to change over time. And so it was like, kind of starting from, like, that's a significant change.
That's a big change.
Yeah.
That makes sense.
Yeah. So then, so I was like, okay, I'm gonna just start from the beginning. And also the other thing is that Kevin, the older Atmos, at least this code, it doesn't reverse chemical reactions. So you can reverse chemical reactions with thermodynamics. And that's really useful for hydrogen emitters, for example, for any gas-rich planet. And it was relevant for my early Earth problem. And so that machinery was really hard to implement. So anyway, started fresh, and this was in the middle of COVID, and I was really lucky to have time. My advisor was very patient, and let me do this for like a year, 6 months. And then for the past, 3 years, wrote it from the ground up. So it's all based on my reading of these older codes, Atmos, the photochemical climate model there. But I tried to get rid of the things that annoyed me, like old PhotoChem stuff. The design of it was inspired by Atmos, as I said, but it was also inspired by this chemical engineering tool called Cantera, which it's so impressive. It's a C++ program. People that are modeling like explosions in engines and or various combustion processes, they use Cantera for that. And it's
That's
like
commercial software.
Oh no, it's open source.
Oh, it is.
Yeah, it's really cool. It's and I've used it before for exoplanet projects. But I'd recommend checking it out if you're interested in just if you're interested in just chemistry in general, like it's a really cool software. And so a lot of like the input files to PhotoChem resemble Cantera. I'm not reinventing the wheel. I followed a lot of their practices. And then it was inspired by a lot of people. Kevin Zonley was the big one. He hasn't written any code, but we have talked a ton and he's helped me a lot. And then a lot of people, including Sukrit here and Ty. So we've been messaging for at least 3 or 4 years. And they've answered my questions. Ty's answered my climate modeling questions. And Sukrit and I have talked about photochemistry. And yeah, so so far the model's been used in a couple papers, 1, 2, 3, 4, 5, and then there's a 6th right here. But out on Monday, I talked about this paper here on early Earth, and I talked about this paper on K2HB. The model was used also on James Webb observations of TOI 270D. The model was also used on James Webb observations of L9859C. Now that you know these planets. And also there's a couple papers that were just accepted. One that looks at
Skylight was just here.
Oh, was it?
Yeah, well, maybe about a month and a half ago, maybe, but yeah.
Yeah, Shognik and I worked on, well, he led the paper. And it's like, effects of planetary parameters on distant chemistry, irradiated planetary atmospheres. So basically, you just looked at like a wide range of parameter space for gas-rich planets and computed photochemical products like SO2. It's like, and then project on early Earth. So now we can transition to the GitHub page. I guess you missed the first bit, but there's this website here with a little bit of a workshop schedule, and so we just did item 1, which is a little bit of background, and then we're going to move on and install the PhotoChem software.
So sorry, what's the link to the website?
Oh yeah, it's right there.
Just that given. Just continuing where you have the code and adjacent.
Yeah. The code itself is the same thing, but it's like that. Nice. Did you guys find this? So did you punched in install code and worked? Did you or
I did, but I did it in another like terminal situation, so I redid it on my terminal on my computer. I think I got it.
you did?
I think so.
Did you get it was the version 0.6?
6.2?
Yeah.
Okay.
Nice. And then wait, yeah. I guess we'll just go over it. So we have this folder here called installation. I click on that. So you can install PhotoChem and other packages needed for this workshop by following the steps below. So for Windows Subsystem for Linux, which you already do, so that's great. And it sounds like everybody here has conduct. So step 1 is perhaps not relevant. And then step 2 is just install the code of conduct.
So I'm not on the network here. I was trying to get in through Edgerome and I can't, so I'll just listen.
Yeah, that's great.
But that's all on the GitHub.
Yeah, you can, this is all, I think, you didn't quite get here, but within all these tutorials all have like completed versions, and so for example, we're going to talk about modern Earth photochemistry, and we're going to start with sort of a blank notebook, but there are completed versions of those notebooks, so you can just look at the completed tutorial, see, this is what I'm what I'm trying to communicate over the next couple minutes. Yeah.
That was good.
So I'm gonna punch in these commands just to do it. So at terminal, I think I have. So I already downloaded this GitHub page, but it's fine. Well, let's kind of create workshop. So I already have it. Just redo it. Have you guys put packages on CondaForge, like Python packages? Python. Yeah, CondaForge is great because it really allows you to do these compile codes. So CondaForge, you upload the code to CondaForge, and then it uses virtual machines or something, some server somewhere will compile it to a binary and then put it on the server. So nobody has to mess with compiling it. You still can compile it, but so this is this new environment, and you'll see all sorts of stuff gets installed, but there's two packages installed here. PhotoChem 0.6.2, and then PhotoChem depends on this package called PhotoChem climate data. So for the photochemical model to operate, it needs like photolysis cross sections, it needs the climate model needs K distributions, various opacities, and those are contained within this other package, PhotoChem climate data. And you can modify this data, but this is sort of like the default cross sections and opacities that so it'll just finish. Activate that environment. Then and so it's worked, PhotoChem version. Did that work for everybody? Or
I was able to install it, I ran into some separate issues where it ran out of files, basically just shuffling things around. Right?
oh shoot.
So, but it's installed.
Oh good. Let's see. Here. Everybody's good online as well? Yeah, just shout out if things aren't working out or something like that. And obviously, yeah, interrupt me at any point. Questions, comments. Okay, so all that works, we have an environment where model will work. So now we're gonna jump to the first tutorial. So at this point, also, everybody should go ahead and if you want to follow along, download this GitHub repository. And you can do that by just clicking code and then do download zip, or you can do git clone this URL link here. And just put that somewhere on your computer in your downloads or whatever. So I'll redo that just for the sake of it. So yeah, I'll do git clone, HTTPS, GitHub, Wogan, Q&A workshop. Yeah.
And it should be in the U of A PhotoChem Workshop directory, right?
Yeah,
Okay,
yeah, it'll that, yeah, so
Great,
then
okay.
I'll and then I'll change directory into that U of A directory and then What, I use Visual Studio Code, what, do you guys use text editors of various kinds? Yeah, so I'm gonna just open this up in Visual Studio Code. This whole folder, so this has all the stuff we were looking at on GitHub, all the different folders, the README that has the workshop schedule. And now we can access like the tutorials in like the Modern Earth photochemistry. So that what we worked out. So I'm gonna run a and then I have a terminal open at this directory, and I'm gonna just run the command Jupyter and make sure that your content environment workshop is activated. Get here. Then I'm gonna go into Modern Earth photochemistry, and I'm gonna open the one that's not. So I'm gonna just wait a couple seconds. So just. Okay, so yeah, here we're gonna model the modern Earth, but it's really just an excuse to like just show you, you know, broad strokes how things work with this model. And so these are just some standard imports: NumPy, Matplotlib, all this plotting stuff, changing the font size for plotting. So the way you use the model is like you use any Python package. So you just say from PhotoChem import Evo atmosphere. So this is like the main photochemical model that we're gonna use. Well, since you guys do gas giants, there's a sort of extension to this that we'll get to later, but this is sort of the vanilla photochemical model. And it's like a Python class. So is our folks generally familiar with object-oriented programming classes?
I mean,
Or translators?
because I've had to struggle with it.
Yeah, you had it.
Yeah, so I mean, you know, I was part of Shami's size. I was his co-advisor from some distance away.
Oh, wonderful.
But he wrote that code. Obviously, I did not write it.
Yeah.
And I mean, I go in there when I try to change things, I'm just like, what in the world is going on? Because it's the computations are all in Python.
Yeah.
The whole thing is in Python. So it's basically convinced me that one should not do calculations in Python.
Well, there's pros and cons, you know, it's interesting to talk about that kind of stuff, but or like Python is so great for like making plots.
It's great for all that
Dynamic stuff.
Yeah.
But then I can get confused in bigger code bases just because everything is so flexible. And the nice thing about Fortran is it has this rigidity, which is a drawback. It slows you down, but I think ultimately to some benefit in the end.
It's faster.
Oh, and then it's
Pure computation.
it's way, yeah, it's completely compiled.
Yeah.
And yeah, Vulkan is great. And I'm at this point, I think I have, you know, as of course you know, Shami made Vulkan, you guys made Vulkan, from the sort of gas-rich planet perspective, just equilibrium chemistry.
From the reversible reaction perspective.
From the reversible reaction perspective, and I pieced together this model from the perspective of rocky planets. So it was like coming, and we've all met, right? Like now Shami models rocky planets, and I am now modeling gas-rich planets. So, and I think we've caught up to each other in terms of, I think I can do gas giant, you know, this model can do gas giants well, and Vulkan can do rocky planets well. Yeah, so you import the model like this, and in Jupyter notebooks like this, you can just put a question mark next to any variable, and it will give you the documentation of that variable. So this says that this is a photochemical model, which assumes no background gas. Once initialized, this class can integrate an atmosphere forward in time to steady state. The model can also optionally self-consist of all planet and terrestrial planets. And then it tells you how to initialize the code. So it takes 4 different files to initialize it. You need this first file, a mechanism file. This is the reactions file. You need a file for settings. You need a file that describes the stellar flux. And then this final file is giving you an initial concentration of the atmosphere and also a pressure temperature profile. And then this is an optional input, data directory. This is like a data folder where the photochemical model depends on UV opacities, for example. And if you don't supply this directory, it will use the default one that you install when you uninstall PhotoChem. But you can supply a directory that you customize the photolysis cross sections or something. So yeah, so we can initialize this by doing atmosphere, and the first input is going to be the reactions file, which will be zonlayer.yaml. So I'm going to jump back over momentarily to our Visual Studio Code. And in this folder, you can see that there's this .yaml file called zonlayer. So this is Kevin Zonley's. This is like my main reactions file, and I modify this for different applications, but this is what I start with. So Kevin Zonley's put this together over many years. So are you all familiar with YAML? You've seen YAML files? Yeah. Yeah, so it's like, think of it as dictionaries and lists. So here we have atoms in this reaction mechanism. There's hydrogen, nitrogen, oxygen, carbon. They have different properties like mass and redox. And then there's species made of atoms. So like hydrogen has a composition, H2 has a composition of 2 hydrogens. And then each species has thermodynamic properties. So these are show-mate polynomial coefficients describing the Gibbs energies. But then you can also use NASA 9 coefficients. There's all sorts of polynomial fits to enthalpies and entropies that you can use.
So if it was a planet without a surface, would it still on bottom of 0 reference pressure?
Yeah, so we will later. We're gonna get to the gas giant stuff, and basically I have an extension to this model where you specify reference pressure instead of 0. Like you don't, a lot of the inputs are gonna look different, and that extension will sort of handle all those details. So yeah, so it is a little bit confusing. We're like, oh, we're gonna model the modern atmosphere, and then we're gonna go to gas giants, and the inputs are gonna look different. Well, of course they're gonna look different, because modeling the modern Earth is just so much different than modeling like WASP 39b. So I have, you have to make essentially slight modifications to the model to accommodate for that. So yeah, we'll get there. So yeah, we have species made with thermodynamic properties, and there's a bunch of them. I've taken files from Xiaomi's, from Wogan, and converted them to this format, and convert some of his networks. So it's very possible to do those translations. So particles. So this is condensed stuff that's not a gas. So here's a water aerosol. It's made of hydrogen and oxygen. Has some density, it has optical properties. It forms from saturation, its gas phase, it's water vapor. And then this is a description of its saturation vapor pressure. And it looks really complicated. It's just trying to get the saturation vapor pressure really good. A very good description of it. And yeah, there's a bunch of different particles, and so many of these are irrelevant to warm gas-rich planets. Water's the main thing that condenses. It's like something like HCCCN is only condenses on Titan.
That's, you have a bunch of Titan stuff here.
Yeah, I do. Yeah. So when I model a planet like WASP 39b, I can just get rid of the stuff. Then like, oh, I know these things won't condense, but I'll leave it in there anyway. Some particles form from reactions. So like in Titan's atmosphere, we can't really model the thing that actually condenses. So instead, I model bigger hydrocarbon gases and then assume that they react to make a big hydrocarbon, which then condenses. So anyway, you can form particles via these reactions like this. I get rid of these for gas-rich planets. They cause problems. And it seems weird to extrapolate haze formation from Titan to a planet with an equilibrium temperature of 1,000 Kelvin. So then there's chemical reactions. So there's a couple different types of reactions. There's fall-off reactions and there's main elementary reactions. So with fall-off reactions, they're pressure dependent. They depend on third bodies in the atmosphere. There's low pressure rate constants and high pressure rate constants. And all like each of these rate constants have a very simple expression. So like the rate constant K would be A times T to the power B times exp of negative E sub A over T. This guys just look just like that. I unfortunately don't have like beautiful read the docs page for this model. It's just really hard to maintain that kind of thing. And I'll get there someday. But a lot of this chemical reaction, the format and the types of reactions, they follow in this whole file. It follows that Cantera software I talked about. Cantera has beautiful documentation. So if I go to modeling chemical reactions, so this is Cantera's documentation. Talk about elementary reactions, and this is the looks slightly different, but like for example, let's go. They say a fall-off reaction may be defined in YAML format using a fall-off reaction type. Click on that and see a reaction that looks like what I just showed you in our reactions file.
So you just use that format for all.
Yeah, I generally use Cantera format. Cantera does some complicated stuff, like you can put special units. I don't do that. I say that I only use units of molecules. I use CGS units.
Okay.
So,
yeah.
For the Zonley Earth .yml file, for the species list where it has like the thermo model and temperature ranges, for the section labeled data, is Cantera also where that information comes from?
Yes, exactly.
Okay.
Yeah. So like if I go up to the species thermo data, so Cantera will specify its thermodynamic properties in a similar format. This information though, these coefficients, they came from the NIST. Well, some of these didn't. Some of these species we don't know very well. We have to estimate them a bit.
Okay.
But a lot of these species, if you go up here, they come from NIST database.
Gotcha.
So like, yeah, you just type in methane NIST, and at one point, I think, you just go to gas phase thermochemistry data, and they give these polynomials right here.
Ah, gotcha. Okay, it was in a slightly different format than what I'm used to seeing. So yeah, okay, I get it now.
Yeah. So yeah, I don't know. Oh yeah, they did give the Show-mate equations here. Oh yeah, Show-mate equation.
We just use that in Ty's PChem class.
Oh really?
Yeah.
Yeah. So yeah, at one point I think obviously you could write a program to extract all these from the internet. And I think Kevin just sat down, went to every single molecule. And it's just like, okay, this number, copy pasted it over. He worked hard. I made sure that he didn't make mistakes. So yeah, and so I'm getting back to the reactions. Oh, a critical part of this is reaction reversibility. So you see this reaction arrow here? It says both ways. If I get rid of that arrow and I just say go this way, and the model will recognize that and say, okay, we're only going to model this reaction in the forward direction, not going to reverse it. Put that arrow in, oops, then it will reverse that reaction with thermodynamics. In general, I reverse all reactions because that means that your model has a thermodynamic consistency to it. But yeah, for rocky planets, the reversed reactions are often super, very, very low rates and they don't matter. But it doesn't add a ton of extra computation time to reverse them anyway. So we go to the very end. And there are photolysis reactions. Molecule plus each new, a photon makes a molecule broken apart. So that's the first of four input files. So the second input file is going to be input settings. So if I go back to the folder, there's this input folder, and here there's settings stuff. And so I guess going back to those on the Earth, that file is what I hope would not change between planets. It's sort of like the chemistry that is true for any planet, any atmosphere. This settings.yaml is like the things that you would tweak between planets. So a lot of this is not going to be relevant for gas-rich planets. So you can probably ignore it because this settings stuff is totally abstracted out when we're going to get to gas giants. But for rocky planets, these settings make a lot more sense. So you have a bottom of the atmosphere and the top of the atmosphere in kilometers, number of vertical layers that you're computing chemistry with, planet mass and planet radius, surface albedo, a solar zenith angle that you're computing UV radical transfer for photolysis rates, diffusion or hydrogen escape is diffusion limited. We don't really think about hydrogen escape when modeling gas giants, but for rock planets, it's important. And then water can be complicated, but all this complicated stuff you can kind of just skim over and generally ignore. This is kind of holdovers from the older models, most of the time I basically turn off all these water features and basically you have the option of fixing the water in the troposphere, and you can give it like a specific relative humidity that resembles Earth. I don't do that normally. You can have gas rain out, so you can have magic rain where gases dissolve and then fall to the surface, and then some rainfall rate relative to modern Earth's. And then if you have some of these settings, you need to specify where the troposphere is. So you don't always need to specify where the troposphere is. If you ignore all these settings, you don't need to specify a troposphere. But basically, the model needs to know where it's raining if you're going to model gas right now. And yeah, water condensation, this is like, the model can do water or condensation in multiple different ways. And basically, this says false, but this model that we're going to run still will have water condensation. So that is confusing. But yeah, water is a complicated one. Yeah. So we're basically turning everything off on these special water settings, except you can have this gas, we're including the rain out of gases and droplets of water with a modern Earth rainfall rate. So then you can specify special settings for particles, for condensables, so like with water vapor or condensed water stuff, I am saying it's going to condense at a relative humidity of 0.5. I'm just doing this for modern Earth because that's what you need to roughly get the water vapor right in the troposphere. But when I model like an exoplanet, I assume, it'll rain out at a saturation, once it reaches its saturation vapor pressure. Just for simplicity. So boundary conditions, so key to solving any system of partial differential equations, you need to say what's happening at the boundaries of the model domain. And so there's a bunch of different types of boundary conditions, but there's two main ones. So the first one is a pressure boundary condition, where you say this is the partial pressure of this gas at the surface in dynes per centimeter squared, CGS units. And just for reference, 1e6 dynes per centimeter squared is equal to 1 bar. So this is 270 bars of water. Of course, we don't have 270 bars of water in the modern atmosphere, but the model will know that, well, water is reaching its saturation vapor pressure, so it doesn't put that in the atmosphere. This is sort of the maximum reservoir that could fill the atmosphere, which is 270 bar. Nitrogen, 0.78 bar, oxygen, 0.21 bar, CO2, this is Earth, pre-industrial Earth, 360 ppm, roughly. And then another boundary condition is a flux. It's not relevant, really, it can be relevant for gas-rich planets, but this is the flux in molecules per centimeter squared per second.
Can you have a flux going into the ground?
Yeah, so you could just put a negative.
Negative, okay.
But negative fluxes can lead to unphysical negative numbers.
Right.
The model will run, but it might blow up.
Light.
Yeah, this is roughly modern Earth's biological flux pressure. There's other boundary conditions. So one thing, I don't know if genetics does this, but some species are very fast, like they change very quickly, and so you can just approximate them to be at like a steady state as all the other species are evolving with time, but then you can approximate some as a
Specific species.
Or we call these short-lived,
Okay.
where they're like
Like your photochemical timescales are really short?
yeah,
Okay.
super short time scale, so we just compute their production and loss and then immediately estimate a concentration rather than try to actually integrate them in time. Anyway, it can sometimes help you get to convergence, to a steady state convergence.
So the old casting code, you had to actually specify which ones were short-lived.
Yeah.
Is that the case here, or?
You do specify, yeah, like here we're saying, mostly with D.
And 2D,
And
right?
yeah, they're both short-lived. The model will work fine with and without these. I don't know.
Because I don't think kinetics, you're talking about the Caltech kinetics
Yeah.
code? Yeah, I don't think it does.
It doesn't do that. Yeah, it's interesting how your casting found that things work better with these, because I've now find that it doesn't really matter.
I would think that it wouldn't matter.
Yeah. I mean, the thing is that, right, the photochemical equations are the reaction diffusion equation is super like stiff numerically, right? Like it is a hard thing to solve where there's vastly different timescales for things changing. Like O singlet D will have a time scale of like less than a second and react. And then oxygen will have a time scale of years or something like that. So I could see how this maybe could help, but anyway. So,
In Jim's early days, probably just had less precision that they were computing.
yeah, maybe that, yeah. So those are the two main, there's other boundary conditions in here, but, oh, and I guess the third one that matters are deposition velocities. So this is just like kind of essentially a pressure dependent, how much gas is getting sort of sequestered into the surface of Earth. And then there is a boundary condition called a Moses boundary condition. There's no arguments. And this is Julie Moses. I don't know, I just read a Julie Moses paper, it's like, oh, that's a good way to do bottomless atmospheres, because with bottomless atmospheres, you want gases to be able to just like be able to mix through the lower boundary. But when we talk about gas giants later, yeah, all of this is generally abstracted away. Like the boundary conditions are essentially for gas-rich planets. When we do for boundary conditions, you just model the atmosphere deep enough into the planet where you reach thermochemical equilibrium, and you fix every gas concentration to be at equilibrium, and then you let things change and gases to quench and change about that. So yeah, this is that's it. Oh, did I did that thing.
So Nick, that was the settings dot, yeah.
Settings dot yeah. And then we'll do input. And we'll do this is the stellar flux file. So this will be important for gas giants. It's a very simple file. It says wavelength, nanometer, solar flux, kilowatts. And this is the solar flux at the top of the planet's atmosphere. So if I integrated all of the energy in the spectrum, it would be at Earth's solar constant, 300 or 1,370 watts per meter squared. That's pretty straightforward. And then the final file is this atmosphere.txt. And this guy is this one here. So this is going to be abstracted away in the gas giant stuff, but rocky planets, it gives you essentially altitude, pressure, density, temperature, eddy diffusion, and then it gives you initial concentrations for all the gases. And this is completely abstracted away. Yeah, it is useful for gas for rocky planets. So yeah, and then you just run that command and it initializes the code. So it reads all these files and it builds this object PC. And so now this PC object, it has all the information relevant to the atmosphere. So so I want to take a moment to go over like how do you access information in this object. So that there's a description of all the species and all the reactions, and then there's like functions attached to this object for doing photochemistry things. So like one thing, a lot of the data is stored in this pc.dat object. So it says this is a class containing data which rarely changes once photochemical model has been initialized. So an example is pc.dat.species names. So when you initialize the model with all these files, you can't change the species names. You can see that, or we could look at the reaction equations. So these are all the reactions now that the model is keeping track of. There's a lot of them. Look at then about 1,300. So then, so there's pc.dat, and then this is information that does not change after initialization. There's pc.var. This is data that can change between independent model integrations. So you might do an integration to equilibrium, and you might change some setting like a boundary condition, and then you will do another calculation. So an example would be maybe the temperature profile. This is the temperature model, each of the different layers, starting from the bottom up to the top. And this could be changed, or the eddy diffusion. So eddy diffusion coefficient. at a diffusion centimeters squared per second.
Can you spell the command with the species again?
With the species, yeah, up here, oh, yeah, it was, like, PC dot species names. Okay, let's print that. Yeah, I guess like one other thing to note is all these variables are documented, so unfortunately, it's a bit hard to access some of the documentation. I need to fix this, but so if I go photochem import. Oops. Photochem data, then I can consider one of these variables. So I can get the documentation string for species names. It says it's a list, its shape is NSP+2. It's a list of species in the model, particles and gases. The last two elements are H2. And so you can look at another variable, like there's this NW variable. This is an integer, it's the number of wavelength bins. So unfortunately, to access these documentation strings, you need to import the pc.dat is a photochem data class. Yeah, that's useful to see what's happening in those variables. So we there's pc.var, and then the final main object is pc.work, pc.wrk. And this class contains data that changes during each step when it integrates the photochemical model. So an example would be like the total density in the atmosphere in each layer. This is molecules per centimeter cubed. This can change. It's generally because it's stable because of hydrostatic equation, but it can change a little bit. Or the main one is, this is a fairly terrible name for a variable, but it's USOL, which is the number densities of all the species in the atmosphere. So if I look at the shape, this is a 2D NumPy array. Its first dimension is all the species in the model, and then it's, all the layers in the model. So an example is I could do something like this, where I say I could get the index of. I can get the index of water vapor in the atmosphere by looking at species names list, getting the index of water vapor, and then I can index the number densities. The first index would be at water vapor, and then I can look at all the layers, and this would give me the number density of water vapor at each layer in the atmosphere.
That's pretty handy.
Yeah. But a lot of this, I don't have a ton of intuition for number densities. So maybe you're like, well, I want the mixing ratio. You could do PC dot work dot divided by the total density. And you would get the volume mixing ratio of water. It's about 1% of the surface. That's as bad as you want. And this is like a complicated way of accessing the concentrations in the model at one point in time. You can also just run this command called mole fraction dictionary, mole fraction dict. And then you can just simply get the water concentration that way. So it's much easier and intuitive way of doing it. So now we just oh yeah. So I'm gonna zoom out, go to the folder here. There is this file utils.py, and it's just got a nice little function here that's gonna make a plot of the atmosphere. And we're gonna import it and use it. So just to go over it really quickly, it makes a plot. It uses that function we just talked about to get all the mixing ratios in the atmosphere. And then it plots a couple species, water, nitrogen, oxygen. And then it changes some scales changes the label, put some labels on it. So at this current state in the atmosphere, we can do import utils. Then we can do utils, plot atmosphere, and we just feed it that PC object. And it gives us.
Can you scroll back up?
Yeah. Okay. Let's do this. And yeah, this resembles Earth. There's some ozone, purple, there's oxygen, nitrogen, water vapor, looks reasonable. Yeah. So up to this point, this has all been just us looking at like the current atmospheric state, but we haven't like done any math on it. It's just been this data that exists in the model. But we want to actually solve for photochemical steady states, right? We want to integrate the photochemical equations to a steady state.
So I think this is just the initial values that are in the model.
These are the initial values, so when you initialize the code, it will read in this file right here, atmosphere.txt, and that's where it gets all these initial
So
concentrations.
okay, so somebody put in actual profiles that are fairly close to actual profiles.
Well, in this
For
case,
some of them.
yeah, this is basically at the steady state of the model, yeah. But if we wanna, let's assume that we're not in the steady state and we wanna get there, then we can just call this function, find steady state. Oh, yeah, we'll just call it.
Can you scroll back up really quick?
Yeah,
I don't know why mine. It says I can't find utils.
You just try to import utils.
And utils.
Oh, maybe you didn't try running that cell above it, I think you,
This one?
yeah, run that guy. And then run the next one.
Okay.
I think it just,
Okay, I see.
yeah,
Okay.
that was big. It should. Yeah, great. Okay, so now we want to find a steady state, we just say there's this function, so there's a bunch of functions attached to this PC object, and you can see what they are by typing PC dot and then tab, and then tell you check for convergence, destroy stepper. There's a lot of these that, you know, maybe you don't need to use, but one of them is find steady state right here. And you can, you know, type in find steady state, question mark, and say integrates using a robust stepper until steady state is achieved. And then returns a variable converged. If true, then the integration is converged to a steady state. So run this model, this function, and it quickly reached a steady state because we basically started with a model that's at a steady state. And it probably printed a bunch of stuff. If you ran this, for some reason it prints. The printing happens to the terminal for me, and for other people sometimes it prints to the print to your notebook.
Can you go back to the?
Yeah.
Okay. Yeah, I printed right here.
Okay. Yeah, it's like showing you integration steps on the path to equilibrium. For rocky planets, the assumption is that we reach a steady state when we integrate to 3 billion years or something. But then there's different criteria for gas-rich planets, because it's hard to get to 3 billion years.
Oh, it also prints my term too, printing those.
Oh, it did not, okay. So we can, just for the sake of making things not crazy, we're gonna turn the printing on. So pc.var.was 0, it'll prevent printing. This function here gets you to a steady state, but you can also just do it like one integration step at a time, which can be really useful for figuring out what's happening in the atmosphere. So there's this function called initialized robust stepper, and you pass it the initial gas concentrations in the atmosphere. So passing it current model concentrations and initializing stepper. I run that and it says, okay, now the model's ready to do an integration. So then you can call pc.robust step. And when you run this, the model takes one integration step and it returns two variables. It says, should I give up or is the model converged? And right now we should not give up and the model is not converged. So we should keep going, one step at a time. And you can see like the model time by looking at this variable here, pc.wk.time now, tn. And so this is the current time we are in the integration. I can take another step and then that time will advance a little bit. And then I can take another step, see how the time is advancing. But it's nice to write sometimes like custom little functions for finding steady states because maybe you want to plot the atmosphere along the way. And so that's what I'm going to do right now. I'm going to write a function called find steady state. And it's going to take in the PC object, and it's going to start by initializing an integrator. And then it's going to make an infinite loop. While true, that's an infinite loop. And it's going to utils, I'm going to plot the atmosphere. Just put some weird stuff here. So this is, you kind of need this stuff to get rid of the previous plot, but we're going to occasionally make a plot of the atmosphere as we march along towards a steady state. And it's going to show it. And then we're going to take like 10 integration steps. So for I on page 10, we're going to say, we're going to take a step. So I'll just copy and paste that variable. If give up or converged, break. And that'll break us out of this for loop. But we need to also break out of this infinite while. And then I'm going to return the converged variable. So did we get to a steady state or not?
I think you had a message in the chat.
Oh, I did. Oh, here you go. Right, it will be available later. Python's acting out for me at the moment. I'm running on my ancient desktop. And would like to try some of this stuff when we have access to my much more. Yeah, we should just talk another time. I'm around the next 2 days, so like, it's no worries. If this isn't working out right. Yeah, okay.
Why is we define steady state, but then we're trying to converge?
We're writing another function for it. Or why are we doing that?
Well, I'm confused why converge is false when we already did run find steady state.
Oh, because I initialized a new integrator.
Oh,
And I hadn't taken enough steps for the model to realize that it's at a steady state.
okay, so you already converged once, and now you're gonna do it again. So
Yeah, and we're gonna
understand.
absolutely, yeah. So yeah, when I run this function, it's just useful because you saw how time is evolving and you can see how, if the atmosphere wanted to change, you could see how it would change. And so if you don't want to write down this function, you can also just cheat by going over to the completed notebook. I think it's written somewhere in here. You can just copy it. Paste it. So, So,
You go back up.
yeah, you're good.
Um.
Yeah, you can also copy the notebook.
From the other one?
If you just go,
Yeah,
home,
I
to
see
your home
this
tab.
one, the
you got it.
work.
Yeah, oh, there you go, yeah, just copy that whole cell. Okay. And so now to actually see something change, I'm gonna change a boundary condition, for methane. So you can do set lower boundary condition, set lower BC. And say methane has a BC type is equal to flux, and flux is equal to 189 molecules per second. Like, and you know, like, obviously, you may not know the inputs of this file, again, you can just put this little question mark next to the function, and it will tell you, you know, the inputs and what's happening. Just remember that you can always do that. So you run this cell and it will change the lower boundary condition for methane to a lower flux than is needed to reproduce the modern Earth. So then we can reintegrate to a new steady state after that changed. And you're gonna see the methane concentration in brown, it's gonna evolve over time. And ultimately we'll reach a new steady state. There we reach a new steady state. So with a low methane. Yeah. And then, so now that's generally like, you know, the broad strokes of how, you know, you get to these steady states and then you're like, well, this is the composition I'm interested in. One other thing to mention, is that, before we take a break is that you may be interested in what's actually, like, why is methane destroyed or why is ozone created? Like what's actually happening in the model. And to access that, there's this function, production and loss. And it computes the production loss of input species. Oh yeah, and it says see production loss object. So that's not the best documentation. But you feed it some species in the model and then some gas concentrations, and then it will return an object describing the production loss of that species. So we can look at methane, for example. And yeah. Oops. And run that, and it does some calculations, and now there's a couple variables attached to this PO. There is the production reactions, so this is all the reactions that make methane. And they're sorted from the most important to the least important. And then you can do loss as well. Loss Rx. And yeah, this is the main loss mechanism for methane in Earth's atmosphere, OH radicals. And then
That's another very handy feature.
it is handy, yeah, so I'm gonna cheat for a moment and copy paste something from the completed notebook. So I'm jumping over to the completed notebook, I scroll down, and we're gonna just grab this plot here. This is gonna make a plot of the production and loss of methane in the atmosphere. So these are the most important reactions making and destroying methane. Right. Methane is not stable in Earth's atmosphere, it's being pumped into the atmosphere from below. So the loss is the dashed lines and it's way bigger than the production. these are just the three most important. We see the most important destruction is OH, apparently chlorine matters, same with G matters. And then production is not very strong. And then we can check that, well, the production and loss in the atmosphere should match the flux that we are putting in. So we can say, well, the sum of the integrated production minus the sum of the integrated loss. And I'll just say this is the total, and I'll just print it. So yeah, there's a loss of nearly 10 to the 9 molecules per centimeter squared per second. And that matches the boundary condition that we set up here. That's the flux of so there's some other stuff in the notebook, but let's leave it there and take a break. Go back in like 5 minutes. And yeah, hopefully that wasn't reasonable. Oh, so yeah, I guess we'll reconvene at like 45.
So I'm over at PSI.
Yeah.
And trying to get edge around through PSI and.
Oh, I did the guest. Did you try UV guest?
I did not try that actually.
So, yeah.
I've on previous visits here, I was told probably not to bother with that.
Oh, yeah. It wasn't, yeah, I don't have the Eddie Rome or whatever. It's Ames Research Center.
Yeah.
But yeah, UV guest.
So PSI edge room's not working right now.
Oh, okay.
ASU, yes.
Yeah. It's you, or UA guest.
I was getting one too.
Well, excuse me.
Edge room. Yeah, I see UA is. I just,
For the first time.
I used it long ago and then never had to use it again.
Yeah.
And now I can't get into this one. But it is handy. Works well, yeah.
I guess, I was wondering, are folks, because next on the agenda is to do some climate modeling for rocky planets. Relatively simple. Climate models can be extended, to James Webb observations, thermal emission observations for rocky planets. So I think could be of interest to some folks here, but, if folks are more interested in, like gas rich, like hot Jupiters or brown dwarf chemistry, we can also transition in that direction. So I guess, where you guys feeling, should we move in the direction of, because we can either do some climate modeling, it actually wouldn't take that long to do that. But then the gas giants notebook reproduces Shami's calculations of WASP 39b. Yeah. What are you guys thinking?
I want to see lots of that.
Yeah, I really can.
Yeah, that's where you're at, yeah.
I defer to you guys because I'm.
Yeah.
I'm getting ready, so.
What about Zoom? How are we feeling? Because we can talk about rocky planets another day as well. I'm here tomorrow and Friday.
So how long are you gonna do this? What's the duration of this event for today?
Oh, the duration is, it's long, yes. So it's until 1.
Till one, okay.
Yeah.
So, because if it is possible to do a short rocky planet climate thing, that would be interesting.
Yeah,
To me at least, right? And then
I think,
the rest of it do all the top Jupiters.
I think the climate stuff will take not nearly as long as the photochemistry. These are relatively simple climate models that I think are useful to just give rough estimates of. And so I think that'll take, we can just kind of go over that pretty quickly in 15 minutes. And then we can finish off with WASP 39b reproducing Shami's calculations. Yeah. So we'll go to folder 4, climate tutorial. I'm gonna do that in my Jupyter notebook. Go back, so climate tutorial, go to this one here. So. Well, so yeah, this just has some standard imports. So there's this climate model in PhotoChem called adiabatic climate. And you import it from photochem.climate, import adiabatic climate. And just down here it's setting some threads. So it's multi-threaded. Not that it matters because it's pretty simple climate calculations. But it's useful if you're exploring and want the calculations to be fast. And you initialize this model, so we can just put the question mark in front of it, gets the documentation string. This class is a 1D climate model, so it draws pseudo-adiabats upward using this equation from Graham's paper, and it connecting an assumed isothermal stratosphere. The model also performs radiative transfer and does nonlinear solve for the incoming solar radiation that balances out on radiation. So for rocky planets, there's simple models and then there's complicated full radiative convective equilibrium models. And this code will do both. It ignores clouds. Clouds are complicated. I'd love to do clouds someday, but not today. Species, so these inputs look very similar to the photochemical model. They're almost, in some cases, they are the same files. So the first file is species.yaml, and I'll just punch them all in here, and then we'll go look at them. The second one is the settings file. It's a different settings file, photochemical one, but it does look pretty similar. And then the last one is stock, solar flux, sun map. If you run that, the model's initialized. So I'm gonna wait a moment and we'll jump out and look at those files. On mine, I can always hit tab if I start typing something. So looking at those files, rid of all the stuff I here, climate tutorial, to input species. This looks like the photochemical species, but it's just the atoms and the species. There's no reactions. But there is thermodynamic information. There's information describing the saturation of these species, saturation vapor pressure of water and CO2, but generally this resembles what we saw in the reactions file, but it just has thermodynamic properties. It doesn't have reactions. And I only have like, I don't know, 8 species in here, the bulk species of planetary atmospheres, but you could copy paste more from a photochemical network. One of those. And then settings file, it looks similar. You have number of layers, the planet mass, radius, number of zenith angles for doing radiative transfer calculations, surface albedo. There's some other settings as well. This is the main important thing for the climate model is the optical properties. So right now, we for when it does radiative transfer, it uses K distributions to approximate line absorption. And those K distributions, there's different ways of dealing with K distributions. Long story short, is this method called random overlap resort within is a really great, I think it's a great way of doing it. It's a good approximation. Then you can specify opacity. So right here, this is saying for K distributions, use all of them. For collision-induced absorption, use all of them for the scattering. But you could specify explicit, like use the CO2, use H2O, use O2, but I always just, I want to use all the opacities, so I leave all those on. So initialize the model. Oh yeah.
So you said it doesn't have clouds, but it does have, it looks like big vaporizations of.
Oh yeah.
Heat, so it does have clouds in that respect.
Yeah, so stuff will condense, but if the rate that condensed material is not accounted for in the climate radiative transfer calculation. So after you initialize the model, everything is somewhat similar in that there's variables like species names. There's water, CO2, nitrogen, methane. That in, and the first thing we're gonna, and there's all sorts of variables in here. So like in function, so one really useful function is there's one of the objects is RAD, R-A-D. This is the radiative transfer that has no documentation string, conveniently. But this is the radiative transfer object that does all the radiative transfer calculations. And so there's all sorts of variables in here. You don't really need to know the details, but it's useful to print like the opacities that you ended up getting. So if I run this function opacities to YAML, it's going to just print a string describing all the opacities that it found. And so it'll look for these opacities in the PhotoChem climate data package that we installed by Aconda. And it found K distributions for these species, it found these CIA opacities and these relay scattering opacities. And this is useful because you could just like go back to the settings file and you could copy paste this whole guy in here. And then if you wanted to see the effect of CO2 on the infrared radiative transfer, get rid of it and rerun a calculation or something like that. Okay, so the first thing to do is we're going to just construct some atmospheres. So there's this variable. We're going to just do some simple steady state climates actually. So you need to specify the surface pressure for all the gases in the atmosphere. So here are the different species. So we need to put a surface pressure for all of these species. And we can just make an array, that's the length of all of the species, and I'm gonna make it an array of ones, but I'm gonna multiply by a small number. 10 minus 10. And I'm gonna find an index of like H2O, for example. And we're gonna set it to 270 bars at the surface. And you can do the same thing, of course. N2, let's make N2 1 bar. Let's make CO2 something like 400 ppm. And in the end of the day, the model needs these numbers in pressures in dynes per centimeter squared. So you have to, since these are in bars, I need to multiply by 10 to the 6 to convert it to dynes squared. So then we need to set a troposphere or stratosphere temperature for this simple climate model. So you say that the troposphere temperature, something like 210 Kelvin, let's say, and then we can call this function surface temperature. You feed it in the surface, these gas reservoirs. So these are going to be sort of, you can consider them as like reservoirs, but in terms of surface pressures, and then you need to specify a guess for the surface temperature. So let's just guess it. Surface temperature is 280. So it's going to spit out the actual. So you run this, and it does a nonlinear solve for the surface temperature that balances incoming and outgoing energy. But this is a simple climate model, and to demonstrate how simple it is, I'm going to need to make a plot of the results here. And to do that, I'm going to steal some information from the completed notebook. So I'm going to just hop over real quick there and completed notebook and steal this. So this is a simple climate model because the temperature structure is assumed to be convecting in the lower atmosphere and then isothermal in the upper atmosphere. This is reasonable in some, many cases, and actually does a decent job to first approximation. And so this is a quasi-steady climate. In reality, the pressure temperature profile would be at full radiative convective equilibrium or look more wiggly in the stratosphere, trying to perfectly balance radiative energy. And so you can do full radiative convective equilibrium calculations with this model by calling this function RCE. So this function computes full radiative convective equilibrium, and you have to give it an array of surface pressures, just like we did for that other function. And then you have to give it guesses for the convecting pattern and the temperature structure of the atmosphere. So I'm actually gonna go back up here, and I'm gonna change. I'm gonna redo this calculation, but I'm gonna change the top of the atmosphere to be at 10 to the minus 4 bar. So with full radiative convective calculations, sometimes the model will go haywire if the top of the atmosphere is a bit too hot. So just to make sure that this model will explode, I'm saying that the top of the atmosphere is going to be at 10 to the minus 4 bar. I'll just make this plot again and see that the top of the atmosphere goes to 10 to the minus 4 bar. So I'm gonna call this RC function, and I'm gonna feed in the current atmospheric state, which is contained within all of the variables in this C object, as an initial guess for the temperature and convecting pattern in the atmosphere. And so I'll run this, and it has to think a bunch because this is a much harder calculation to get full radiative convective equilibrium.
Can you go upvote?
That's
Yeah.
Put that word down. Nice. If I could, I'm gonna copy this plotting script and run it again. And you'll see that you get a more wiggly temperature profile. The temperature structure looks different. It's much colder than this one, block, where we assume the stratosphere is at 210 Kelvin, and then this actually computed full rate of
Ozone.
Can you go to the?
Oh, yeah, no ozone.
Can you go to that one line right above the C, RE, yeah.
Right there. Yeah, exactly. Ozone would make the inversion, but no ozone. It's calculation. This is your generic habitable world. Nitrogen, CO2, water. Did that work?
Yeah.
Chug it away. Or-
Mhm.
So yeah, that's like the super fast intraday climate modeling for rocky planets. And I use this RCD model, like these thermal, like in Tom Green's thermal emission calculations of like TRAPPIST-1b, no atmosphere stuff. You can do these like heat redistribution parameterizations and tack them onto this 1D model and then estimate the emission you'd expect under different atmospheric scenarios. Not that there's any atmospheres to interpret at this point. There's nothing detected. But if there were, and still you can put upper limits. You can say, well, it doesn't look like the data is compatible with CO2 greater than a bar, whatever. But yeah,
Was this plugging into the photochemistry?
They
Is it
can't.
doing photochemistry right now, or it's not? Oh,
so yeah, this is only the climate, and you can, so the way I normally do it, so it's hard to compute like full climate photochemical equilibrium. So challenging things to do. But so normally what I do is I get an estimate of the climate based on the bulk composition of the atmosphere. So I say, oh, there's some CO2, maybe some methane, and then I compute photochemistry on top of that. So there's this function that I use where I can like output an atmosphere. So if I need to give it. Quickly show you that one. So this produces a file where it looks exactly like the input for the photochemical model. So it puts out this temperature pressure profile. You have to specify additivity, and I just put in one sort of this model would actually run, but that's not what it is. And then it gives you initial guesses for all the gases in the atmosphere. So you could, then set boundary conditions resembling this in the photochemical model, and you could do photochemistry on top of this. And it's somewhat realistic. It's not. In principle, I would love to someday have be able to compute a fully self-consistent atmosphere, but that's
a pain in the neck.
it's a pain in the neck.
Yeah.
And for rocky planets, it's especially hard because condensables are very hard to deal with. Like water vapor and CO2 on habitable planets is totally annoying. And for gas giants, you can just ignore water. Life's great. So that's
How hard is it to add ozone to this calculation right now?
It's, so, yeah, I mean,
Not too hard.
not terribly, I mean, well, it is a little hard.
Okay, don't do it.
Yeah, I wanna do it, yeah. But it's possible, yeah. But yeah, so, we'll leave that there and let's just charge forth to, if it sounds okay, we'll go to Wasser and IB. And we taught, with the photochemical model, we learned how it worked, and of course, I'm gonna just, before we go to Wasser and IB, I'm gonna go to the source code and just kind of show you what's happening here. So the photochemical model, I need to make extensions. I needed to make an extension for gas giants. So I don't know if you guys are familiar with like extending a class in Python, like object-oriented stuff. Basically, I take in, this is the main photochemical model, and I make this new object called atmospheric gas giant. And this just adds the functionality to make gas giants easy, because what we worked with earlier is just hard to do gas giants. There's, it's just a huge pain. So this gives it the functionality so that you can just like quickly, okay, punch in a metallicity, a C to O ratio, and it will do those calculations fairly rapidly. So, so long story short is, there's a bunch additional methods attached to this new class that we'll go over that make it easy to do an atmosphere like Wasser and IB or ground door. Yeah, so let's now go into the notebooks, go to extra tutorials, and then there's gas giants and ground dwarfs. Gas giants. Yeah, so so as I just said, PhotoChem has this extension. Did everybody find this notebook? Good. Okay. It has this extension called the EVO atmosphere that makes it easy to simulate gas giants. Basically, it makes it kind of like Vulkan. Vulkan's very easy to do gas giants. And this tutorial demonstrates how to use the extension by reproducing the photochemical SO2 in Wasser and IB's atmosphere, described in Sean's paper. And here are some planet and stellar properties. Oh yeah. So what we're importing NumPy, matplotlib. This is just a plotting thing. AstroPy, we need some constants. Photochem.utils import. Yeah, this is I sort of trim away some unnecessary stuff when that Kevin saw in his reaction file. That is like the big file, and then I strip it down for certain applications. So like chlorine, for example. I don't care about chlorine for this application. Slow down the model, so I get rid of it. But I keep all the other systems. And that's what this function is going to allow us to do. We're going to just trim away atoms. Photochem, and then we have to import photochem.extensions, import gas giants. So this is the extension. It's going to make it easy. And then we got some properties for Wasser and IB, like the radius, the mass, the equilibrium temperature. Oh, and then we have a stellar radius, stellar effective temperature, stellar metallicity, stellar log G. I'm not sure why we need this. Yeah, I don't know why. We don't need this. So run that. What should work. So yeah, this file, or this function is this nice function for trimming down the reactions file. And here I'm saying I want the atoms hydrogen, helium, nitrogen, oxygen, carbon, sulfur, but I'm leaving out. And then this is going to produce two files, and I'm just specifying the output file name, photochem reactions.yaml and photochem thermo.yaml. And this thermodynamic file is going to be useful for it's gonna look almost the same as the reactions file, but in a slightly different format, and that's gonna be for the equilibrium solver. That's gonna give us initial guess for phos-390's atmosphere composition. And then, yeah, remove reaction particles. So these, you definitely want to always leave out particles that form by reactions, because that is a bit weird. So you run that, and then if I go to Visual Studio Code, oh, not that one, but this one, if we go into tutorials, gas giants, you can see that it produced reaction thermo. It's just, it's like what we saw earlier with Kevin's on these reactions, but trimmed down. And this thermodynamic file is going to look about the same as well. Oh yeah, so this is important. So for fast chemistry can sometimes slow down or prevent the photo model from reaching a steady state. So sulfur chemistry in particular is often problematic. It's mostly problematic for planets much colder than WAS-390b though. So WAS-390b is hot. For whatever reason, things are a bit easier when concerned. And so it might be hard for the model to converge in some cases. So if you don't care about sulfur, then just get rid of it when you make these files. And also you can just remove some of these fast sulfur species. So if you don't care about S3, S8, and S4 sulfur aerosols, and they're not going to be important for warmer sub-Neptunes. Like, I mean, they're important, but they're not the most important thing. They may not, I don't think they would be, detected by James Webb. And I don't think leaving them out would affect the chemistry too much.
That might not be right.
What?
That might not be right.
Well, it depends on the planet. Yeah.
The sulfur chemistry, the allotropes of sulfur are all quite abundant and high. So you can get a whole variety of them.
Yeah. Well, yeah, so like in.
And they're also very hard to detect.
Yeah.
Because their infrared signatures are crappy.
Like in K218b, which is bold, these are really important. Like it's something I didn't talk about on Monday, but like there's a ton of like S8 is very preferred, especially when you get older than 600, 700 equilibrium, KF equilibrium temperature. So main sulfur reservoir might be S8, and then S8 might even condense and form clouds, which should happen on K218b. And I don't understand why there aren't obvious clouds on K218b. There's no evidence of it in the spectrum though. So yeah, so definitely for cool Neptunes, but I think you would get about the same answer for SO2 if you deleted some of these guys, but maybe, I mean, it would have effects certainly. So now we're going to initialize the model, and this looks different than what we saw before because we're using the extension. And so here I'm just computing planet mass and radius in grams and centimeters. And to initialize this guy, I'm going to just put a question mark in front of it. So it takes in the necessary arguments are the reaction mechanism file and the stellar flux file, just like we did previously. And then it instead takes in planet mass and radius, and those are the only four necessary files. And then under the hood, it's going to deal with the settings and the atmosphere file. Like it's going to essentially deal with that under the hood. And then there's some optional inputs that are relevant here. So I have a reference pressure, for example. This is 1 bar or 10 to the 6 centimeters squared, or dynes per centimeter squared. So integral, scale factor, blah, blah, blah. One of the important files is the thermodynamic file. So there's also an equilibrium solver that's going to be called under the hood, and you need this. Here I'm passing it a dedicated file. Oh yeah, and the solar zenith angle in Shami's paper, he says 83 degrees, so that's fine. So I ran that, and I also there's a bunch more, there's this new, so before there was pc.dat, pc.bar, pc.work, and I've added this new object that probably has no docstring, unfortunately, will someday. And it has all this new data attached to it that's needed to do these gas giant calculations. Like an example is bottom of the, well, that's a bit confusing. Like top of the atmosphere average pressure. This is in dynes per centimeter squared, so let's or divide by 10 to the 6. So you can change this number, but the model's going to try and keep the top of the atmosphere at 10 to the minus 6 bars. That's generally not a crazy value. Or bottom the atmosphere pressure factor. This is a value that says that there's these parameterizations for when we think there should be an equilibrium to disequilibrium transition, right, at depth in the gas giant atmosphere. And we can estimate essentially at what pressure level we know. We don't need to model down to like 10,000 bar with the photochemistry. We can model down to 500 bar or even 10 bar if the planet's hot enough, and still capture all the necessary chemistry above there. And so what this is saying is it's going to go a factor of 5 pressure deeper than we think the deepest quenching should occur. If that makes sense. That might definitely some jargon, but yeah. Oh yeah. So another critical thing is when modeling gas giants, we all assume that the planet has some composition relative to the sun, right? Helicity. And the model has this, it has the chemical equilibrium solver in it. And right now we have some default composition of the sun. It's based on one of the common it's like a 2009 paper, I'm forgetting the author. Anyway, this is the composition that's assumed for hydrogen, nitrogen, oxygen, carbon, sulfur, helium. And this is reasonable, but Shami uses a different one in his 2022 paper. So this little code block here is just changing the composition of the sun to be identical to what Shami assumed, just to make sure we use it. So, yeah, bit complicated here, but there's this variable here is showing the assumed composition of the sun. You just need to set it, and so that we can go over the details of this. That's valuable, but not species. So now these atoms have these concentrations. That's what they assume the solar composition is. Okay, next we establish several key variables. So we need to say what is the pressure temperature profile, and here we use them. Shami has this warning profile described in this paper, computed with the GCM, and then you need to specify a KZZ profile, and we're going to just use what Shami used. So altitude or pressure dependent KZZ mixing. Then you specify a metallicity, so Shami used 10 times solar, and a C to O ratio. Shami used the solar identical to the solar. So that's what's happening here. We're reading in a file that Shami used from the GCM for the pressure and temperature, specify the KZZ, metallicity is 30 times solar, C to O ratio is 1 times solar. And then next, we take all that information and we feed that to the photochemical model in this function initialized to climate equilibrium pressure temperature. What this does is it goes and it basically just grids up the atmosphere and computes equilibrium and gets an initial guess and sets everything up to do an actual calculation. And now we're just ready to integrate to a steady state. just like before, we initialize a robust stepper, and then here, this is gonna call, there's a lot going on here, so it says for an infinite loop, it makes a plot of the atmosphere, and then it says every 100 steps, or for 100 steps, to take an integration step, and then if give up or reach a steady state, then we're gonna break this loop. And this takes a bit. So yeah, this is starting at it's sort of an yeah. So SO2 is purple, which isn't shown up. It's very close to the shown.
You may have mentioned this, but what time roughly, like what order of magnitude does the model converge at?
Like how long would
Yeah.
it take?
No, I mean like in
oh.
simulated time.
Simulated time.
Yeah,
Simulated time, I think it'll be 10 to the 10 seconds.
okay,
Something like that. That's like 1,000 years.
okay.
That's a good use. Oh, there we go, SO2. Making that out itself. And I think I turned off. In the integrator, it will sometimes restart. So you'll be like marching along at some time, and then it's gonna be like, oh, I need to restart. And it does that because sometimes it gets stuck. So it's like, oh, let's try to restart it and tweak things a little bit. So I'll hold up. Shows this figure. Yeah, once we get. Yeah, the solar zenith angle is, like, in the case of this model, it's imagining that it's computing photochemistry relevant to like the morning, yeah. So that's where it's doing the UV radiative transfer, the zenith angle, that it's doing the UV radiative transfer to compute photolysis rates. And it does turn out that you really need to put in this 83 degrees to reproduce on these. Like you just put in a sort of a global average of 60 degrees. Then you know right into.
So it's like almost, so just 7 degrees above.
Yeah.
It's very slight angle.
Yeah.
Otherwise, it might produce, if you do the day side, like traces or substellar point, it might be.
Yeah.
way
If you
more
put in,
fluid.
yes, 0 degrees, then you would break a lot more molecules with UV. Yeah. It's hard to know if that would make more sense to do or something.
So he didn't run cases like that? That he did?
Oh, I bet he did. But I think he, and maybe he did in the paper, but the main results were 83 degrees.
For comparing with observation?
Yeah, so here's his, so he did 2 calculations, one in the morning, Terminator. In the morning, he got this profile, so what is the peak of his SO2 is going up to just under 10 to the -4 at millibar. This is a bar. So that 10 to the -1 millibar is 10 to the -4 bar. So this looks about right. I'm getting roughly the right amount of SO2. And everything else, like I get photolysis of H2S, I get that a lot deeper than, and this spread is like, I think a couple different models. So H2S is really destroyed in my case, or in this case.
So yeah, your cliff is at 10⁻² bars, isn't where, he's in millibars,
Bars. So
10 millibars.
this would be 10 to the minus.
Yeah, so it's the lower part of that.
Yeah, so my cliff looks kind of like the bottom edge. And yeah, so you could, I mean, I've punched in, you could just fairly easily punch in different planet mass and radius, and you could generate a UV spectrum for any other planet, GOI 270G, any of the planets in the Planetary program. Well, I know you guys have Lindsay, Mike Line, Lindsay, we're doing Wogan observations.
Yeah.
Yeah. So yeah,
So what is the lower boundary condition?
oh yeah, this is actually, yeah, this is actually confusing to describe this. So I'm gonna just make the plot, I'm gonna so see this blue line right here? This is the bottom of the photochemical model. And its photochemical calculations are happening there and above. And then it knows that it should be probably equilibrium below that. So all the everything down here is just computed by an equilibrium solver. And I think above here is photochemistry. And so the boundary pressure, the boundary conditions at the bottom, they're all set to be identical to the equilibrium result. Yeah, that's the assumption. And this is all kind of happens under the hood. So I'm gonna scroll up here a bit. Yeah, in this function, initialize to climate equilibrium PT, a lot of stuff happens in here. One of which is it will set all the surface boundary conditions to be at equilibrium chemistry. And yeah, I guess I can plot a comparison with equilibrium as well. There's these added functions here, return atmosphere, equilibrium true. So this is returning the atmosphere at either the photochemical prediction right here, or it's computing chemical equilibrium to the atmosphere, so you can compare. So these faint dotted lines, this is the equilibrium result. Different. SO2, of course, equilibrium, 0. Very close to 0. Yeah, so this function is actually, so PC dot return atmosphere. And it just returns a dictionary of pressure, temperature, Z, and then all of the gases in the atmosphere. Okay. H2O, there's H2O at each of these.
That is a really helpful feature.
Yeah.
Being used to having to wrangle that data out of Atmos using a lot of kludges.
Yeah, the old model that we used had sometimes the gases were there's 10 rows of gas concentrations and then it would wrap around. It was the craziest thing I had to read from a file. Yeah. But yeah, Shognik, I guess some of you guys know, he took this and he explored various sort of Wasser 9b atmospheres and looked at all sorts of photochemical and disequilibrium effects, and so yeah, I've yet to, and then the K2HEB stuff that I talked about on Monday, these kinds of calculations. But yeah, I think it can be applied. And then I've done ground dwarf. So I don't know, do you know Ben Liu?
I don't.
Okay, he works at NASA Ames, Wogan. I think previously worked with, or has worked with Mark Miley before, but you get involved doing some ground dwarf calculations where I use the same thing, but obviously there's no UV photons coming from the
Right.
top. So I just feed it a UV flux file that has like 0 values. So it's still computing radiative transfer,
Yeah.
but not having any effect. I should just have a switch that says turn off.
There's a little interstellar UV you could include.
I think that's a good point, yeah. But yeah, and so you can do that for outdoors. But the quenching approximations from Kevin's only, he put those together in 2014, and they do work very well. It's amazing. And things will get weird in this model if you go to cold planets and then you go to high metallicities, you get all sorts of crazy things that can like condense and like if you go to 1,000 times solar metallicity, the model principle should hopefully work, but then all sorts of things are going to want to condense maybe. Like if it's a cold TOI 270b or K218b, especially K218b, water is going to condense. You're going to produce sulfur species that want to condense. If you're in an even colder planet, then yeah, ammonia is going to condense.
But well, depending on temperature, that kind of metallicity, you're gonna have metals also. Like you would have other things, SiO,
Oh yeah,
a whole magnesium iron, all of that sort of stuff could come in. Again,
Yeah.
depending on.
so this is another challenge is in reality at depth in Wallace 9B's atmosphere. Like, I mean, the temperature down here, what is it? It's like, I can current atmosphere temperature and look, yeah, 4,500 Kelvin at the bottom. So obviously there are things like SiO and all these actual metal things, rocky things, that condenses out somewhere in here, right? And we don't track that, and that's because that sounds hard. It's possible to do that, but I've never done that. And so sometimes what we do is we say, oh, well, we know that SiO, we know that silicon species will condense out and sequester some oxygen. So then we account for that by kind of reducing changing our solar abundances a little bit to reflect that condensation, but we don't actually model it. That's sort of our rough approximation that I've done. Yeah. And generally, Shami and I have prepared a ton. We get generally the same answers. Nice. I'm sure there's differences, but the general broad strokes seem to work out. I guess like one other thing, yeah, this is actually very important, is the model hopefully will converge all the time, but it may not. And there's 2 variables to mess with. So there's an absolute tolerance of integration. So what this says is that if there's a molecule less of a concentration less than this value, then the part of the integrator that determines the time step size, it will not account for those low concentration species. And that's important because you don't necessarily care about species that are at 10 to the minus 200 concentration. They're just going to slow down the integrator. You need to say that essentially something is 0 at some simple number. But you don't want this number to be too big because then the integrator will not, will take too big of time steps and everything explodes. So 10 to the minus 18, like for gas giants, I find that this value for Wallace 9B, this probably works really well, but maybe, you'd want to try 10 to the minus 17 or 10 to the minus 19 if you're like, wow, the model's running and not converging. I mean, Shodnik was somehow able to run like thousands of models and it works. So hopefully that means it'll work most of the time.
So is that a mole fraction effect?
Essentially a mole fraction, yeah. So if we plotted down to like down to 30, we took a look at something that's super trace, like yes, 2 trace. maybe 2 trace. Yeah, so you can see that this is the O2 profile in light blue, and see how it's like probably going to a negative number here? Because it's saying, well, this is below the absolute tolerance of 10 to the minus 18. So it doesn't really worry about that. Like in negative numbers, small negative numbers they kind of have to be okay with them. Like what's the, we can look at, let's see, look at the smallest. Actually, so if I look at, I'm gonna look at the smallest negative number. Or I guess the largest magnitude negative number. So that I have a negative number somewhere that is a mixing ratio of 10 to the minus 22.
It's a nice search feature too.
Yeah. Whatever. That's such a small number. I don't. Yeah. So and then so that's one number to tweak with. The other thing to mess with is there's this switch auto diff. So auto diff. Oh, this you can't put a question mark there. So auto diff is activated to true. So for the integration, you need to compute like a bunch of derivatives, the Jacobian of the system of photochemical equations. And that can be done via finite differences, which is a very common technique. Make a calculation, you change something a little bit, make another calculation, and then you get kind of an approximation of a derivative. Or there are other techniques. Wogan uses symbolic differentiation, where, yeah.
Crazy shot.
It's crazy, yeah. So what Wogan does is it uses this PacSymPy, where it will read all the chemical reactions and then it will literally write an analytical expression for the derivative.
That's crazy.
It's crazy. You look at these, the resulting Python file, and it's like, okay. And so, and I don't do the symbolic stuff because code generation doesn't. It's harder with Fortran and we can compile stuff. So the two things I do is the first one, which is finite differences, and the other option is auto diff. Do you guys know auto diff technique? Auto diff is this. When I learned about it, it's freaking magical. It's crazy. It's basically uses the chain rule at a very, very high level to compute derivatives very accurately, like to within machine precision. So by default for the gas giant stuff, I use this auto diff calculation of the Jacobian, and it works very well. But every once in a while, for some reason, it doesn't work well. So sometimes I turn it off, and and when I turn it off, it uses the finite difference method to compute the Jacobian. And for some reason, that gets you to convergence. These are mysterious things. Yeah, and let's continue on the things that are hidden under the hood actually. So first, computing steady states, we got to 10 to the 10 seconds about, and that wasn't like the Rocky Planet where we got to billions of years. There's a different method here, and this method actually follows Wogan exactly. So what Wogan or this gas giant does to determine convergence is it saves the integration steps of the past 500 steps or whatever. And then it looks throughout that history and it tries to see if the atmosphere is changing or not, and to what degree is it changing. And if it's changing by some small percentage, and the default value, you can see there's these variables. This is the main conv long d1. It's the exact same variable name actually. This says if this is the threshold, if the change, well, there's another one. If conv, so there's this conv history factor. What it does, it says let's look back at. So if we're at time 8 times 10 to the 9, we're going to look at time that divided by 2, so 4 times 10 to the 9. And we're going to compare the atmosphere between now and back then at 4 times 10 to the 9. And then we're going to look, has the atmosphere changed by more than 1%, 0.01? if it has changed by less than that amount, we say it's conversion. But if it's more, then it's like, oh, we gotta keep going. Keep chugging away. So if you're like, I'm not happy with this, you could set this to a smaller number. Smaller threshold. Or if you're like, wow, I'm never getting convergence, maybe you can be happy with putting in 5% change. Yeah.
So you usually run at 0.1.
I use, this is what bowling by default, I think, so. Oh yeah, and instead of doing all that plotting business, you can also just do this same function, find steady state. But we're gonna set it to true. And I think, yeah, so we're just restarting where we left off at the steady state, so it just took us a couple steps to determine that, oh yeah, we're at state. So yeah, that was obviously a ton, but thanks for bearing with me. So at this point, if you have any more questions, obviously hit me with them. But there's also on the website, there is a survey that I was supposed to share. So go ahead and take that. Obviously, I think that I told them this is what we're going to talk about, and obviously we changed that because we're interested in gas giants, and so there'll be some irrelevant questions, I think, but more or less, some of this should still apply.
All right, let's see, Nick, I'm at your GitHub, but remind me where that workshop is.
So, oh yeah,
Appreciate it.
yeah, for sure. So see this URL right here. Is that visible?
Oh, yeah.
Okay.
I'll see you Friday. I think we're getting lunch. I think
Yeah.
I'm eating lunch. Okay, I'll see you Friday.
I'll see you then, yeah.
Ah.
Yeah, like one of them. Where did the climate simulation be produced in Habitable Zone? Say in
Yeah, we did not do that.
so easy.
So easy that we didn't do it. Travel 27 is fun, but you guys probably know better than me. The observations won't make them. Come through. Maybe someday.
Gonna try.
Yeah, might as well, of course, try.
So Nick, where do I say? My experience is with the 1977 version.
My feeling is a little, yeah, we'll never be here.
Yeah.
Whatever.
First question is fun. It is funny though to see the USOL show up.
Yeah, that's from
It's
1980.
from the old, yeah.
That is a Jim casting variable name that somehow.
I never quite understood where that came from. It's a
I'm
weird
pretty
name.
sure it comes from like when I've seen in applied math textbooks, when they talk about methods for solving ordinary differential equations, U is the changing variable. So I think that's how we start. So
Could be.
I don't know, that's my theory.
I'm hitting not applicable for some of this because they have it on the,
Sure. The survey, yeah, I'm not really sure who's doing it. I don't know. I got an email that shares.
Want to do the evening, morning.
Oh, yeah. Yeah,
So if you wanted the evening, you just need a different temperature profile.
yeah,
Everything else would be the same.
yeah, it would. So there's this folder, subfolder here, and it has two PT profiles.
Okay.
Yeah, we just didn't do the evening. But yeah, just punch that in, create the flies, and then,
Assume the seating thing will be the same, as it doesn't really care which side of the air.
yeah, it doesn't matter, or it's symmetrical.
Yeah, because Matthew has some interesting differences, these strong asymmetries. SO2. Exactly.
Yeah, let's see, there it is. For whatever reason, you're looking at,
so what, that's, yeah, sorry, that's morning and evening right there, right? I
Oh.
didn't actually get to go back to that nature
This
plot there, yeah.
yeah, so we did this one, and then there's the evening that we are doing now.
Right.
For whatever reason. Yeah, a little bit less SO2, just above 10 to the minus 5, and this one is more like 10 to the minus. I think I get a little bit, ever so slightly less. Right after. No.
So
It looks similar. Less.
Wow, this I thought photochemistry is hard. And it was, I mean, so many things, there's something like
Well,
controversy that on planet science that are not, not resolved. It seems like remarkable that you're getting the abundances within the factor.
Nick, click on that. Yeah, so is this a 2D calculation?
no, this is a 1D.
You're sure?
I'm sure.
Because he has, so what's he changing then from evening to morning?
Just the pressure temperature profile. It's the only difference.
Okay.
Um,
Presumably the winds are carrying.
Yeah, agreed. So you didn't do that?
Oh, I just changed it. So the first thing that we did earlier was the morning, and right now I punched in the evening. Pressure temperature profile, and now it's just making its way. Being made it, so. I'll get the.
Oh, yeah, I was looking at the wrong curve. So they're both purple.
Well, yeah, I mean, I don't know, there's one of the models has this little bump. I mean, I don't think that would be observable, I'm not sure. Maybe it would.
That's in an essay. I don't know how you're gonna see it.
Oh, let's change that. Yeah. Let's go. Same. So. So. And then, yeah, I mean, so yeah, why do they agree? I think because like. You look at the path to make, I mean, main critical reactions are largely I think, well, this must be super well known. It's like H2O reacting with H, making OH, like from sort of combustion processes. Like this, to me, this is an important driver because then to build up the oxidized sulfur species, you need these OHs. And so Shami does say in his paper that like he does expect there to be a drop off of SO2 production as you go to colder climates because this reaction itself it slows down quite a lot when you get colder. So you're making less OH. So that means you're not as able to produce that SO2. I think it's kind of where he does like a simple, relatively simple calculation. Here we are. Yeah, so he's looking at that one rate. I think that one reaction. Water, hydrogen atom, making OH. Showing how that is falling down as a function of temperature. So he then says X species dominate over the SO species down here because you're losing out on that OH. And then that pans out when you do the full calculations. Oh wait, are these full calculations? These might be full calculations. Average mixing ratio between 10, 0 and bar. So SX species are dominant sulfur species. Here, they are recessive. Yeah.
Although we see it in
I can do that.
700K planet.
Yeah. It's for a 7 and 2D 30%, but that seems to be far older. Technical, I would agree, but. Yeah.
But I think with Vulcan, I mean, they did the Vulcan
It worked out.
parameters and were able to make it, right? And so maybe this was compensated by extra metallicity.
Yeah. I imagine that you could turn knobs and change this cliff to some degree.
What were the reactions again? You showed the little packet of reactions.
Big deep in the figures. Yeah, he was saying that's a critical one. OH. So yeah, it's just shows us
So it's H2S conversion to SH, the S atom, and then reaction with OH. Yeah, it's interesting.
And this is like to figure these net paths. That's when I use that production and loss guy that we talked about earlier, like production or actually loss. Actually, we'll look at yeah. So the production of OH, look, the dominant production of OH is H2O plus H. So yeah. The dominant.
So that is at a specific altitude or that's integrated?
This is the integrated column. That's how it's sorted, but you can look at it as a function of altitude. So there's this is just going to be a giant array of all those reactions. Anyway, you have to kind of like, yeah, you can look at it as a function of altitude.
Right.
It's interesting that there's a sort of, the second reaction on that list was CO2 basically doing the same thing that water's doing here.
Oh, was it?
And I've noticed that like CO2 can be pretty temperature as well, somewhat in step with the SO2. And I wonder if this is part of the reason.
Yeah, so you can go, let's see, so you can just copy this guy and then go in here. Oh. Yeah.
Endothermic reaction. A little bit.
Yeah, and then we can do OH. So this, oh, see now, the production loss is huge in hot atmospheres, so you go. This is probably what matters. So it's interesting at depth, so you can see that like this first, the biggest production, this is the reverse of the first. So blue is the production of OH, and then this is the reverse of that, and you can see how those are matched.
Yep.
So they're in equal, you know, that reaction is equilibrium, unbalanced sort of thing, almost. And then the CO2 one, it looks like it matters, but it does seem it's smaller. I guess it just makes sense, less CO2, right? Probably proportionally, this ratio might be proportional to the relative CO2 versus water. Maybe. Yes. And then we can do like, what's the H2S? Loss in. So loss is H plus H2S, which was the first one that mattered. H2S. And this is, I spend way too much time, sometimes you're like, well, what the heck is happening in this model? And so I'm like, okay, what's making this, what's making that? And I like try to build, you know, these things, you know, these net reaction paths. Like, okay, that's how you get from here to there.
You have to do.
Yeah, you have to do that, you have to, and then you're like, wait, is this? I run into chicken and the egg problems all the time, or I'm like, wait, is this making that, or like, where did this come from? So. Yeah, thank you guys. Nice. That's fun. Yeah, love